So starting with section 1.2, which has to do with graphs of equations in two variables. And we're going to look at graphs, equations, and also talk a little bit about intercepts and symmetry. Here it says that graphs play an important role in helping us visualize the relationships that exist between two variable quantities. So if we are comparing two quantities, like distance and time or time and cost. For example, in this table 1, it's an adjusted average price of gasoline in California for the years 1978 to the year 2005. Now, if I zoom in on this a little bit, if I just wanted to know, okay, how much does it cost in the year 1990? I can go and here I can look. But it's really difficult to see what's happening to the price of gasoline over time. So sometimes it's better to look at this data represented in a graph. Okay, so here we have the price of the gas is our y-axis, and in the x-axis we have the years. So here we're comparing time and price. And we can kind of see what's happening over time. The gas went up, it went back down further, kind of stayed the same. But this gives us a better representation of what's happening over the time period that we have. All right, so that's just a reason that we look at graphs when we're dealing with more than one variable. All right, so in example 1, we have some review of algebra here. We want to determine if the following points are on the graph of the equation 2x minus y equals 6. All we need to do to determine that is take our x value and our y value and plug them into the equation for x and y. So if I rewrite the equation with the variables replaced with the values, I have 2 times 2 minus 3 equals 6. Oops. 2 times 2 is 4 minus 3, that equals 1. So this was the equation. When I simplified the equation for this ordered pair, 4 minus 3 is 1. That does not equal 6. So this means that this point does not satisfy this equation, and that point would not be on the graph of this equation. So we would say no. If I do another one, let's plug in 2 and negative 2. So I have 2 times 2 for x minus negative 2 for y. Does that equal 6? So I replaced my x and y with the values. Now I'm going to simplify. I have 4 minus a negative is plus 2. That does equal 6. So this point, 2, negative 2, yes, it is on the graph of this equation. Then I have the ordered pair 4, 2. So I have 2 times 4 minus y is 2. Does that equal 6? Well, this is 8 minus 2, and that is 6. So I can say 6 equals 6, so yes, this ordered pair is on this graph, or this point is on this graph. All right, a little review in graphing equations. All right, so I want to graph an equation by plotting some points. So what I need to do is pick some x values. And Really what I want to do is I want to have a couple negative values. Let's pick -3, -1. We always want to look at 0. And then let's do 1 and 2. So now I'm going to take the x value, plug it into the equation. So I have 2 times -3 plus 5. That's -6 plus 5 is -1. So this represents the point -3 for x, -1 for y. Now I'm going to plug in -1. I have -2 plus 5 is 3. So this is the point -1, 3. 2 times 0 plus 5. 0 plus 5 is 5. 0, 5. 2 times 1 is 2. Plus 5 is 7. And 2 times 2 is 4. Plus 5 is 9. So this is 1, 7, and 2, 9. So now if I'm going to plot these points, notice my x values, -3, -1, 0, 1, 2. I need to put them on my x-axis. Let's make sure that when I'm counting, these spaces are as close to being equal as we can get. I can label these -1, -2, -3, 0, 1, 2, 3. So this is just a number line. Now the y values also have their own number line. They don't have to be the same distance apart as your x values, depending on what your y values are. So I see that I'm going from -1 to 9. So let's say this is 10 up here. This is 5. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And -1. All right, so notice these values are the same distance away from each other. They don't have to be, you don't have to use the same axis or the same distance between point to point for x and y axis. So I'm going to plot these. This is -3, 1. This is -1, 3. This is 0, 5. This is 1, 7. And this is 2, 9. So I'm just trying to get them as close to an estimated spot as I can get. And I'm going to draw a line to connect the dots. And we have a line that represents this equation. So these are some sample points that are on this line, but remember that technically any point that lays on this line satisfies this equation. Okay, the x and y values plugged into this equation would make a true sentence. All right, so here's another one. Again, I want to pick a couple negatives. How about -2, -1, 0, 1, and 2. And then I'm going to square them. So this is -2. I'm going to square it. I get +4. This is -1. I'm going to square it. This is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. All right, so I need again to label my axes. So 1, 2, 3, -1, and -2. And I need to label my y-axes, going from 0 to 4. So 1, 2, 3, 4. These look about the same distance apart. Now I'm going to plot my points. So I have -2, 4. That would be up here. -1, 1. 0, 0. 1, 1. And 2, 4. So if I were to connect these points in a curve, any point that's on this curve would make this a true sentence. Okay, so just a little review on how to graph equations. Next thing we're going to look at is intercepts. So an intercept is where the graph crosses an axis. Okay, so the x-intercept is any point that intersects the x-axis. And it's represented by the ordered pair x, comma, 0. Anytime we have an x-intercept, the y-coordinate is 0. So let's just pretend over here, if I'm counting and I wanted to label this point, this would be over 2, up 0. Okay, this would be over 3, up 0. So any x-intercept is going to have a y-coordinate of 0. Y-intercept is any point that intersects the y-axis. Okay, so if I'm looking at this, and let's say I label this, I'm just counting here. If I wanted to name this point, this would be over 0, up 3. Anywhere on the y-axis, my x-coordinate is going to be 0. So this is going to be 0, and then wherever it crosses the y-axis. All right, so looking at this diagram here, we want to find the x-intercepts and the y-intercepts. So if I look here, and I'm going to zoom in real big, the x-intercepts are where it crosses the x-axis. So I'm going to just name those points, which are -3, 0, 3/2, 0, that is this one right here. I'm going to zoom back out so you can see what I'm writing. There we go. And then 4.50. Okay, so 3 x-intercepts. Now I'm going to look at the y-intercepts. Here I have 3 y-intercepts. And the first one, I wrote over that number. The first one is 0, 3. The second one is 0, -4/3. And the next one is 0, -3.5. Okay, so there's the y-intercepts. Excuse me. Example 5 says to find the x-intercepts and the y-intercepts of this graph. So I'm going to do this without graphing. So the first thing I'm going to do is I'm going to find the x-intercept. And I know from back here, if I have an x-intercept, I'm going to have an x value and the y value is going to be 0. So I can plug the y value into the equation for y. So if y is 0, y equals x squared minus 4. Now I'm just going to solve for x. So if I add 4 to both sides, 4 equals x squared. To undo the x squared, I need to square root both sides, and x equals positive and -2. So this one is going to have two x-intercepts, and one is going to be the x value that we get when we solve the equation, positive 2, 0, and the other one is going to be negative 2, 0. Okay, so those are the x-intercepts. Now to find the y-intercepts, remember from above, the coordinates of a y-intercept is 0 for x and then the y value. So this time I'm going to plug in 0 for x. I have y equals 0 squared minus 4, and 0 squared is 0 minus 4 is negative 4. So this will only have one y-intercept, and that's at the point 0, negative 4. All right, so we're going to just touch a little bit on symmetry before we're done. And we know that symmetry is kind of like a reflection. So if I see something that has x-axis symmetry, okay, or if I want to see if a graph is symmetric about the x-axis, this is our let's say our original graph, and if it's flipped over the x-axis, the distance from the x-axis to one point is going to be the same as the distance from the x-axis to the reflected point. Okay, so we can see here that the x-axis is cutting this graph right down the middle, and every point on one graph is going to correspond to a point on the other graph. Okay, so this is symmetric about the x-axis. If something is symmetric about the y-axis, we're going to flip it side to side. For the x-axis, we'd flip up and down over the x-axis. For the y-axis symmetry, we'll flip it over the y-axis. So every point on the graph corresponds to a point that is the same distance away from the y-axis. Then we have this symmetry about the origin. And if we're talking about symmetry about the origin, we're talking about a point that goes through the origin, and in that line has a point that is the same distance away from the origin. Okay, and that line is actually called, I'm going to draw this in here. This is the y equals x line. So this point through the origin is symmetric about the origin if the reflection is the same distance. Okay, here's one. I go to the origin and I reflect it the same distance. This point right here, if I go to the origin and continue on in that line to another point the same distance. Okay, so this just kind of talks a little bit about symmetry, and in our second part of this lesson, we're going to look at symmetry a little bit more in depth.